Fuad Abinader. I am a research engineer at the Nokia Bell Labs Paris site. And I'm actually working with Professor François, Chad. And I was asked to give a presentation, so I thought that it would be nice if I could come here and talk a little bit about the subject research we are working there, the field of standardization of 5G. So, just a disclaimer, this is not supposed to be a tutorial on MIMO or beamforming. We are basically here trying to explain how beamforming, and MIMO and beamforming specific, became a central piece of 5G. It was already present in previous versions, since 3G already had some form of MIMO. But with 5G, for the first time, it became like central, to the point that the whole system was created from the ground up to be, let's say, beam-based. And also, my intention, I'll present you the basic procedures, but I will talk at the end, not slides, but I'll try to give you my personal view on what are the main issues that we are dealing right now with research. So it's more like a conversation than a proper tutorial. But if any of you have any questions at any moment, just you can stop and ask for free. Okay? So today's presentation, since I know not everyone is a person in the telecommunications in this topic, do a little recap on MIMO and beamforming, and its role in 5G and R, which is the Hierarch phase. Then talk about two basic procedures, which are very important, and where the main focus of the procedures for being management implemented on the initial access, and after you enter on the system, the maintenance, what they call beam management. Yeah, so that's more or less what you're going to see today. And at the end, I will give my personal insights on this. So, quick recap. Again, it's not a tutorial MIMO, but just recap that MIMO means multiple input, multiple output. It's just the idea that instead of having a single antenna for transmitting and another antenna for receiving, we can have multiple. And why that? First of all, each antenna, each path between a transmitter and receiver, if you do it properly, by doing properly means you use the proper different distance between antennas, which depends on the frequency you're operating, etc., and the antenna size. If you do it properly, every single path between a transmitter and a receiver, for example, from transmitter 1 to all the receivers, you have a different channel realization. This has the potential that if you transmit the signal properly, there's some pre-coding for doing this. You can have, later, for example, you can sum up the signals and increase your SINR. Or you can transmit multiple paths, different versions of the data. For example, part of the data goes one antenna part goes in another antenna, and then you increase the throughput. So you can do multiple things. Another thing that you can do, you can try to, using, for example, phase shifters, you can try to create like an effect that you direct your signal specifically for a direction with high gain, which is called the beamforming. So you can do multiple stuff with this technology. And this is not the intention of the presentation today, this is more or less the field that we are happy. But before we continue, I need to talk a little bit about antenna array architectures. Yes, we can have multiple transmitters, multiple receivers, but we have different ways of doing this. So the first way we can do this is every single signal we are going to transmit to each antenna, we have a transceiver. We have a transmitter reception independently working. Sorry. And we can adapt the waves. We can adapt the signals we are transmitting. We can implement frequencies slightly beamforming in the way that we can part of the frequency in the carrier are going to transmit on beam in one direction, part in another. We can do multiple stuff. We can also have on the other side what they call analog beamforming, which is basically, for example, you apply some smart shifting on the signals for the antennas, but you only have one transmitter and receiver. one signal. And then you just try to point it to a specific direction. And you can have something in the middle which is called hybrid beamforming. So the idea basically is that for lower frequencies, it is feasible for you to use digital beamforming. Lower frequency, I mean below 6 gigahertz. For above 6 gigahertz, when we start to go into millimeter wave, what is more practical is just to use analog beamforming. This will play a role. Then I'll explain later about the initial access. But again, just to give you a brief idea of what we are talking about. Then MIMO in 3GPP is not new. It's by no means new. It is present since release 8. So even with 3G, we already had ASQ plus you already had some form of MIMO operating. And when the introduction of LTE, it also have been there. Maybe had the transmission mode 8, transmission mode 9, even COMP. COMP is a way of, in release 11, it's a way of having, for example, instead of having the same base station transmitting different signals, you can have multiple base stations transmitting together in order to increase the SINR for the received signal. Requires some special X2 connections between the GNOBs, but it could be done. COMP is something that is in with LTE for some time. And but the problem is that until release 15, it was, let's say, it's kind of a patch, because the system was not designed from the ground up to be beam-centric. With LTE, we already had a lot of support, because when we had the reference signals, we already had some support for from the control channels for monitoring the channels, but the control channels themselves were never transmitted in beamforming. We could only do this for the shared channels, for the data channels. And with 5GNR, from the ground up, including the control channels, everything, the whole system is beam-based. And why would we do that? We have a number of challenges with 5GNR that we need to face. So in terms of capacity, this is well known. Most macro networks are already quite congested, and we are running out of capacity on the spectrum. The good spectrum, which is the one below 3 gigahertz, the one where we have less pathloss, and we have far more reach, and we have coverage issues. So, for example, there's a desire that, okay, I don't have a spectrum below 3 gigahertz, but I have a spectrum above, and I would like to have the same site that I designed for a spectrum that is lower to be using a spectrum that is above. So, if there is a direct relation between the frequency carrier you're operating and how far your signal goes because of the noise at the receiver. And so the propagation decreases with the frequencies decrease. So you cannot design the same sites you had for 2 gigahertz you cannot use for 6. Because if you don't do anything else, just changing the operation, because the coverage size will be way smaller. So if you want to do this, you will need like some gains from the beamforming. Above 6 gigahertz, then you do have a lot of bandwidth, but then you also have poor pathloss conditions. I told you there's this frequency issue. There is also a lot of absorption from the atmosphere, from the higher frequencies, the oxygen absorption and things like that. That will make it more. You have more like it makes more complicated for operating higher frequencies. Then also we have active antennas right now. For example, for implementing the phase shifters, antennas are no longer these passive peripherals. They have some intelligence there. And 3GPP spec, as I told you, because of all those factors, from the beginning, from 5G, it was decided that, okay, because we have all those challenges and we need the gains from beamforming, we are going to make the 5G new radio, which is radio interface, beam sync. And I will translate this in into what it actually constitutes. Okay. So in terms of the challenges we have for massive MIMO higher frequencies, because the gains are for operating higher frequencies, because we have a lot of available bandwidth in higher frequencies to operate. While we have limitations, like sometimes depending on the country, for example, 2.1 megahertz frequency, we have channels that are sometimes 100 or 200 megahertz that you need to divide among all the operators. And then you have the auctions, and they pay very expensively for this portion of spectrum. When you go for higher frequencies, you have gigahertz of available spectrum. You also have the auctions, but it's way more bandwidth that you can make use. Okay, you have limitations of reach, but we have tools like beamforming to help us. So one of the challenges is poor pathloss. You need to make use of a large number of antennas, because with a larger number of antennas we can generate a large number of beams with high gain, and that we can point to the direction of the user. And but the problem is that to make use of this, you need to collect a lot of feedback. This is another big problem. Obtain knowledge about the channel, so you sending sounding, referencing nodes that you measure and report back. This takes a little bit of signal spectral efficiency. This takes a little bit of time because you need to filter it. You need number of measurements. And then there's the cost, because if you go for full digital, as you saw, digital beamforming, you have a transceiver for each antenna. This means that we have a power amplifier for each antenna. We have a modulator, demodulator for each antenna. This is a lot of energy cost, which is already something that is quite problematic. So, especially when we go for higher frequencies, when we have larger array of antennas, it's not really viable to have one transceiver for each antenna. Then you need to go for analog beamforming or hybrid approaches. And the main thing here is that the main challenge is, okay, we know all that, we are going to use beamforming. So how do we design from the ground up a system that can operate, that assumes you're always operating using beamforming? And this is basically what we are going to present to you. This is the main challenge. So
this complex discussion is for data transfer,
control as well.
But what was the initial access?
I'm going to.
How do you read the...
Yeah, I will get that. So I'm just explaining to you why it was like this from the ground up. So the idea is that we need to design a system that will support both lower and higher frequencies with the same mechanism. So it needs to be flexible. It needs to support both FDD and TDD. TDD, it's easier because you can assume reciprocity, so the same channel that goes in downlink is the same channel in uplink. FDD is a little bit more complicated, but it still can work. So you should, as I'm saying, support full digital array, and also analog architectures. We have now something called multiple transmission reception points, TRPs. So you can have, for example, multiple radios working at the same time on your mobile phone, communicating with different antennas, for example. And so we have multiple what they call TXRU configurations, and it supports all of them. So UE, we can have now multiple panels. So a mobile phone like this can have now, for example, 6 panels, different panels, and work in different ways. You can have just one baseband, so you need just to select the panel, or you can have multiple radios and can operate multiple panels at the same time. So all of this needs to be incorporated in the design of the system. And you can use this either for capacity or for coverage or both. So finishing the recap, about to enter into the actual topic. 5G NR beam-based operation is a design principle. By that, it means that from the beginning, from the moment you acquire the network, and you want to enter on the network, you already operate based on beamforming. You already need. The challenge here is that because we do this, it means that I will monitor different beams when I'm doing the initial access, and this means that I need to stop and read the different beams and report back what's my decision when I do the initial access. And after I enter the network, I need to continue doing this. So there is some delay, and there is some signaling that needs to be done for this to work. And this is the challenge. It's the overhead that we add. Okay, we are going to make use of beamforming for everything, but we add this overhead. Then now we need to cope with this overhead, and we need to use smartly the mechanism to have at disposal to cope with this overhead. So as I told, in LT we already had some support of beamforming, even from control signaling for monitoring, but now all the control channels, everything is transmitted using beamforming. And even if you have one, what they call TRP, or multiple TRPs. So you can have situations like this that I'm describing here, where I have one terminal that might be receiving 3 beams from 3 different cells. If I'm a mobile phone, for example, have 3 baseband, I can be transmitting 3 data channels independently to the mobile phone. So, and again, that, as I already told, the terminal, in the past you always assume that the terminal is a omnidirectional antenna. Now you not only assume that you can have beamforming on the terminal side, but you can have multiple panels. So this means that the procedures that I do for monitoring the channel should be done both on the GNB side, the downlink side, but also on the receiver side. This also adds delays because I need to measure the side, everything like this. It's also a challenge. So, and actually this is one of the topics that we are right now researching, is when we have multiple panels in one terminal, do we need some special support from the network or not? So this is the subject I'm right now doing my research, just for you to understand. At the end I will explain a little bit more. So about the initial access. So synchronization signals are the ones that, for example, when I turn on my mobile phone, it will start looking at the frequencies it was configured to operate. This comes in your SIM card, for example. In your SIM card, when you connect on, you read what are the frequencies I should look for. So Orange will tell me to look at this frequency. And when I look at this frequency, what does it mean? In 5G and R, it means that differently from the other networks, previous versions, I will not find every signal I want in the center of the carrier frequency. Up to 4G, okay, so the carrier is 2.1. I know that if I look at the center of the carrier frequency, I'm going to find the signal there. This is no longer true, because with 5G and R, I think in Andrea's presentation 3 weeks ago about bandwidth part, that she explained that the SSBs can be located in different portions of the spectrum. I need to do a raster search, and in this search, not only I need to do the raster, but in each part, I'm looking at the frequency carrier. I should listen for the different beams, because what's going to happen is there is the introduction of what they call synchronization signal block, SSB, which is a compact way of transmitting the primary and secondary synchronization signals. The signals that we are going to monitor to synchronize in time and frequency, and also what they call the master information block, which carries the description of that carrier. So you're going to, so what happens is periodically the network transmits these SS blocks, and it repeats. And every time it transmits using different beam direction. So it's going to do like this, you repeat, and the idea is that I monitor, and the UE chooses the beam that I got the best reception.
The UE is operating
can be operating normally or can be operating with beamforming. Doesn't matter, because at this moment, what you are doing is choosing the downlink beamforming.
Yeah, but I mean, does the UV have the possibility to do beamforming right
Yes.
away?
Yes, but it's not at this moment. There is a procedure called P3, which is can be done after it initiates. This is the P1. I will enter the number.
Okay.
So,
And then secondly, when you say there is a pattern of PSS, SSS in beams,
yes.
is it a well-defined standardized pattern, or it can be anything?
Can be anything. So the 3GPP just dictates that if you want to do the transmission of SSB, you should do in blocks. And these blocks have this size, which depends on the numerology.
Yeah.
Depend on the numerology. And I will explain later here. But the point is that how you choose to which beam to transmit at each moment, it's up to implementation. So you may say maybe it's better that I do a sweep like this, or maybe I do a binary search, or I do repetitions of the same. So one block I just transmit one beam, it's up for the implementation. And this is actually a problem, because when you want to design a good system for doing beam monitoring, you don't know what to expect. You can think of one configuration, but each operator can decide to do whatever.
So, I'm sorry, I don't want to just monopolize the time, but I mean, how would you manage to implement this with something like URLLC?
You're going to get it.
Okay.
But it's obviously not going to matter for your LLC, at least in the initial implementations. It's more like reservations, like some persistent locations. Yeah, but we are already talking about using beamforming for this. Obviously, it will require some extra effort in terms of signaling. So you will need to allocate a lot of reference symbols for monitoring, such that your LLC can use that. But yes, it might be an issue. Because it implies delays. Because if I need to monitor different beams, I need to read all the different beams, and I need to assume that I have some filtering. So just not the first measurement that make the decision. I will make maybe 3 measurements, 5 measurements, apply a filter, and on the filtered version make the decision. So it presents some challenges. No. You're going to come to them. So this signal, it has a very limited definition in terms of time space, 4 symbol time, and 240 carriers, so 20 PRBs. And it may number of beams that I can transmit this signal. This is the same signal transmitted over the different beams. The only difference is that each time it transmits for a different beam, there is a relation between the SS beam transmitting in a beam and the RACH code I'm going to use in uplink as a terminal to indicate to the network which is the beam that I'm choosing. So every time I'm transmitting, associated with that beam that I received in that moment, there is a moment in time on the uplink in a specific RACH code that if I transmit, the network will know, oh, you are referring to that beam. So the way that you choose the beam is monitor the different SSBs, you get the RACH code, which is transmitted there and the SSB, and then the network knows you are referring, oh, you want to use this beam, so we are going to talk over this beam. This is transmitted, as I said, there is a period, time that repeats and then transmits every X milliseconds, 20 milliseconds for example, and then I can have what they call the burst of the SSBs, which lasts 5 milliseconds. Within this 5 milliseconds, depending on the numerology, the subcarrier space and symbol time, I can have a different number of SSBs that I can transmit, so from 4 up to 64, depending on the numerology. And within this block, I transmit them serially with some spacing. And I can do things like this. Every time I transmit one of those blocks, I transmit using a different beam direction. And I'll be monitoring on the other side, maybe, not, this is really terrible for me, improving, better, this is the best one. So because this is the best, and this is the best, this is the one that I'm choosing. So, and how do I do this? I do what the procedure called 4-step watch, which is used for initial access and for cellular selection, and for radio link failure recovery and many other things. So the idea is I'll monitor the different beams, different SSBs, and me as a terminal, I will choose the best that I realize it, and I report back using the RATch code, which is something like this. Every associated beamforming, I have a pointer in time, in frequency, and code of what is the RATch code I should use to inform the network that that beam is the best one for me. So I will choose one of those and report here.
So what does the RACH code look like? What is it?
It's a Zadovshu code. So you have yes. So you have a bunch of orthogonal codes, and you choose one. Okay. No.
These are
Sorry?
These are randomly selected parameters.
The network can select the codes and allocate them for the different beams. But when you choose, you're going to transmit the Zadovshu code indicated for the beam you selected. Because it's like this. This is the only moment when the UE has some power to determine what is the best beam for it. Because after it enters the network, then it's the genome bit that keeps selecting what's the best beam. So sorry.
But the question is like the choice of the code is random.
You have a limited set of Zadovshu codes.
Yes. So you may have high traffic that collision.
You may have collisions.
You have
Yes.
talked about this.
No, we are not exploring this, but you may have collisions.
Okay.
You do definitely may have collisions. But you have a very high number of Zadovshu codes. But it's still, it's one point in the system where you can have collisions. And if you have collisions, you need to try again. Yes. So the RATch code is, has a specific moment in time and frequency. You have a specific code. When you transmit there, it's like a reserved resource where you indicate for the network, hey, I am a terminal, I want to enter in the system, and I want to use this beam, because this beam is associated with this RATch coding and this moment in time and frequency. And then when the network receives this, okay, I have resources to receive you in my network, then I will allocate random access response for you, and I will say, okay, you need to proceed with message, this is message 1, message 2, you need to proceed with message 3 and 4 with, on this channel, on this moment in time and frequency allocation. I can do this negotiation, that's my 4-step. 1 step to route, 2nd step confirmation with the allocation. Here you indicate what, I am terminal X with this, and this is my code and everything like this is my password, then and confirms you are in the network. But all of this is transmitted over the beam that you selected when you transmitted the RATch. So this is what is important here, that from the beginning, I monitor the beams, I select the beams as a terminal, and from the moment I start doing initial access, everything is conducted on that beam I selected. And it keeps in that beam until I enter the network, I started measuring the reference signals, and I report back to the network, and then it's just the network that informs me what's a new beam. As I move, I will have different optimal beams, and I will monitor the reference signals for the different beams, and report back to the network that the network will select. But the moment in which I can do is initial access.
So the sweeping that you showed, so it was for one base station basically.
Yes, and you do this
You do this for all base stations.
Yes.
And you select the beam of an E base station, which is the best. Or can you do this for you are looking to?
Actually, you continue doing even after you enter the system, because when you monitor the neighbors' networks, if you are in 5G, you are doing the same thing for the neighbor cells, because you need to know what is the best beam for each neighbor cell as well. So you see that with 5G and R different from LTE, the requirements from monitoring increases. You get the benefits, but you get the cost also. So it increases a little bit amount of monitoring you need to do. That's why, for example, they chose to start implementation with with 5G as a secondary carrier in an LTE network. Because then you would get the cell coverage with LTE, and you would use just 5G NR for high throughput. Because this procedure is expensive, and they decided to delay a little bit. Now, see deployments where this is like standalone, but the initial ones have no standalone, because this is expensive. You do this not only for yourself, for the neighbor cells as well. Okay? So, yes?
Do you know how we can apply this on two-step patch?
Two-step patch is actually used for beam failure recovery. Beam failure recovery. When you fail the beam and you choose a new beam, I will explain, it's also there. But we do have, this is the four-step patch where you do this very expensive search and negotiation. And the two-step patch here, I'm going to talk about beam failure recovery. So, once you are in the system, you selected your beam, you did the initial procedure for message 1, 2, 3, and 4, using selecting the RAT code for transmitting uplink, then you get a random access code, random access response, and did the message 3 and 4. You are in the system. You are now a slave to the G-node beam. You no longer make decisions for yourself. The beam selection is going to be decided via TCI allocation from the G-node beam, based on the reporting that you upload, transmitting uplink. So again, this was the initial procedure. The main thing here to remember is that the initial beam selection is done by the UE and is kept over the initial access. Once done at the initial access, that beam, selected beam, is kept until the G-node beam selects a new beam. So the only moment where the UE can select a beam is here, the initial access. Then everything relies on this, measurements and reporting. So we have the layer 1 measurements. We have a set of what is called reference symbols. We have different reference symbols. The most basic one is the SSB, which I just mentioned. But we also have channel state information reference symbols, CSIRSs. We have tracking reference symbols for localization. We have different types of reference symbols. But the ones that matter for us for this purpose are the CSIRS and SSBs. We can have up to 64 configured individually for each UE, which means we can have one for each beam allocated if we want to monitor. If the UE supports, actually can go up to 128. So you can imagine how much overhead, because each one of those reference symbols is a portion of time and frequency that I occupy, allocate for transmitting control, signaling, and not data. So this is an overhead. So yes, I can have more beam tracking, I can have more, but it comes at the cost of spectral efficiency. But we do believe that we have gains, because if we use beamforming, we can have like really high gains, we can transmit high modulation, and it can pay off.
So, I mean, to say earlier, so, I mean, if the UE has a bidirectional antenna, so you're not guaranteed to decode the beam information that is sent to you.
You can have,
You could have, I mean, you could have much more interference than
yeah,
signal,
you
right?
can.
And so there is a chance that especially for, I suppose, narrow signals, if you have many sectors, okay, that you, in the other case I don't know, but there is it's not guaranteed that you detect the best beam which is directed to a particular time.
Yes, especially because you may not have a direct path, yes, for example, and you don't have the gain from the beamform like the 6 dB or 12 dB.
To decode the
Yes,
information.
but you still have the gain from the transmitter side. You have the gains from the G-node B side, so you have the 6 or 12 dBs of gain on the transmitter side. Obviously, it gets better if you're on the receiver side. You don't have only, you have direction panels, and actually that's the direction that these terminals are going. It's not, you no longer assume they are omni, you assume they have some, at least some gains, and that's why you spread panels over the mobile terminal. If you buy a high-end terminal, that's what you have today. But just to say that it can work with, even with omni. But the idea, obviously, yes, you have different panels, direction antennas, you have the gain also on the UV side. But this comes at the price that I need to monitor each one of those panels, all those beams in each one of those panels. I need to do the search and then do my choice, so it's slow. So the more panels you put, the slower it becomes, unless you pay the price for the energy, for having multiple transmitter receivers and do this at the same time.
So all the beams, I guess it's a sweeping beam rather than multiple beams which are stationary, is that right?
Yes, every time you transmit one SSB, you transmit one beam.
So in every direction, the beam has the same gain, same directivity, or
Not necessarily. Not necessarily. If you look at the pattern of the beams that transmit, for example, on an 8x8 panel, 16 by 16 panel, you see that the central beams they are more well shaped and they have higher gains. And when you go more for the beams in the side of the panel, they become a little bit more, first, the more wide, and they become, the gain becomes smaller.
And between two cells, different cells, different cells can have different beam gains, or?
Yeah, they can have different antenna configurations. Yeah, it's
Okay.
it's
I guess you have
it's a challenge.
No, I guess you have some performance analysis.
Not here in this presentation. We do have results. We can have another presentation where I can present them. And actually, it's going to be because it's about mobility. It's not only about intra-cell mobility and inter-cell mobility results. And we are doing this analysis for FR1 and FR2. We can, it works. It just has the price of the delay. And then we present what's the cost. It's the problem is that it works quite nice in FR1 below 6
Please
gigahertz.
carry on with your talk. I'm sorry to interrupt.
No. But yeah, we need to collect those measurements and report. You have a different configuration. We can report. All the reports are configured by the GNOB, so the GNOB tells you you're going to monitor this resource and this resource and this resource, which is some symbols transmitted in specific time and frequency. And you report back the measurements, what is the RSRP that you're reading for those. And based on those, it will make its decision. We implement this into what they call hierarchical approach. This is the way that everyone is implementing. That we have two levels of beams. First level, we have very wide beams. Like if I have a 120-degree sector, we can have, let's say, 4 in FR1. 4 beams, very wide beams. Those are 2. Depends how you configure your network, your antenna configuration. But and on those wide beams, you're going to transmit the SSB. So I'm transmitting one SSB here, 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 and here. And I only need to monitor those 4 beams and decide between those 4 beams, do the initial access. Once I do the initial access, I go for more refined beams. So I can make more narrow beams. So if I cover one wide beam, and inside this wide beam I can have 4 narrow beams, supposedly. And to monitor those, I will transmit specific reference symbols called CSIRSs, these narrow beams, which I'm going to monitor, report back to the GNOB, and the GNOB will select among those 4, inside the big one, what they're going to use. It's like you're doing binary search. You choose the first level, and then inside that level, I choose what's the net. And I can do it multiple ways. Usually people are implementing 2 levels, but you can even implement in 3 levels, for example, with different width of the beams.
So once you are looking at the beam and report the beam, it's also that there is a very fast object.
Yeah.
That is
Not only the terminal itself is moving, But the environment,
And in the environment also.
yes, correct. Sometimes even some foliage comes in front of some tree. See, you pass in front of a tree, that tree might already completely destroy your channel.
Or a truck.
Or truck, if you think mobility, now you think on cells that in 5G, they have this idea of putting cells inside poles, light poles. And you're passing light poles, so you're moving very fast. How do you cope with this? With the procedures we are going to explain here. Because we still have like the rate link monitoring, rate link failure, which is a procedure that's very old since GSM. But we have a lower and faster mechanism called beam failure detection, beam failure recovery, which works like an intra-cell mobility. Because radio link monitoring is for inter-cell mobility, when I leave a cell and I did not enter on the other cell. If I'm inside a cell and I'm moving between the beams inside a cell, it's like mini cells, like intra-cell mobility. There are procedures for monitoring this. But this, again, comes at the price of monitoring and reporting. Because it's all based on the measurement. So these measurements become essential in 5G now. And the filtering you apply, nothing of this is standardized. So it's up for you to decide how you implement the filtering. So this is essential. This is essential part for getting 5G and right with beamforming. I don't know if I answer you. It's going to explain you in a few moments. Yeah. So we have these two procedures. P1 is the one I mentioned. When I select the white beams, then I continuously monitor and select P2, which is the procedure when I select what's the beam that I should be using. I monitor all the beams, that refined beams which transmit CSI-RSs, report back to the network keeps, okay, this beam become best for you. Use this beam, use this beam. And then answering your question, I can also have beamforming on the UE side. And then I have a procedure called P3, where for the beam I was selected, whether wide or narrow, doesn't matter, I will select autonomously what is the best receiving beam. I don't report back to GNOB. I will monitor my receiving beams and I will select my one. And
So does it make sense? So speaking of the detection of the signal, so could the UE fail at P1 and succeed in P2, or it's you have to succeed first P1 and then
if you don't succeed P1, you are not in the network.
you're not in the network, right?
Yeah.
And so then, okay, but you could detect the P2 thing and report.
Now what happens is when I enter the network
Alright.
might decide, it's not mandatory, but it might decide that I want you to use a narrower beam. And that for this, if you necessarily allocate reference symbols in those narrower beams, inform you to monitor those narrower beams in those reference symbols. You spend some time monitoring those. Probably you apply some filtering, because so you're not reacting spuriously. You measure the field time.
Excuse me. For P1 it's clear that it is the node G node which is doing the beams.
Yes.
And in P2 also,
Also,
the beams are under control of,
GNOB. Always GNOB.
okay. And how would G node be decide whether in P2 it wants to have one beam, two beams, three beams, or how many beams?
This is schedule decision. It's completely open. Implementation decision.
So it all depends on what is the bandwidth and what is the link budget can you want
Yes,
to set.
and my antenna configuration, what's my policy, if this user is really important for me, for example, if it is URLC, maybe I want to allocate a number of different, for each beam that I want you to monitor, I need to allocate a reference symbol. If I want you to monitor 16 beams, for example, I would allocate 16 reference symbols. I would spend,
When you say I, it is the G node B.
yes, GNOB.
Yeah, but okay, that's not the point. The point is that the G node B has decided to make 4 beams in P2.
Yeah.
Okay. And then the UA has to start all over again.
shows the beam 3, white beam 3.
Yeah.
And I'm continuing using, my data transmission is going there, my control channel is going there. But while I'm doing this, I'm also monitoring the reference symbols in parallel. I don't stop to do this. I monitor this and I report in the CSI report. And based on this, the GNode B may decide. You may decide never to switch you to a narrow beam because your measurements say it is not worth. Because you need to remember, if you are talking, for example, in analog beamforming, in FR2, it means that when I allocate some transmission for you, the whole transmission, that TTI, is going to be transmitted in that beam. So I'm reserving.
That is clear.
Yeah. And this is, I'm spending some resources with that.
Here we are still in the initial access phase.
No, initial access phase finished here.
I see.
So P2, I'm already in the system. I'm already with PDS-CH allocations, having data transmissions. I have some CSIRS.
How does the mobile know that it has to look at beam number 2 rather than beam number 3?
No, the GNode B, you configure RC measurement elements, objects, and those measurement objects are necessarily either CSIRSs or SSPs. And the CSIRSs that the GNode B configures for the UV to monitor, they are going to be transmitted in beam 1, 2, and 3 level. So it's the GNode B that configures you to measure those beams at a specific moment in time and frequency. So it's always the GNode B that configures you to measure. And if it configures you to measure, when it's the time and the frequency, it's going to transmit in that beam, in that direction for you to measure. Does it make sense?
Okay. Actually, my question is more related to P3 rather than P2 because...
P3?
Yeah, because I mean, if in P3 the base station is not making narrower beams.
No, it may be, doesn't, you have some beam here.
No, either we are in this P2 or we are in P3. We can't be combination of P2 and P3.
This is done to initial access. You may use this, this is optional.
No, I mean, as far as the UE is omnidirectional, then it can receive from 1, 2 or 3 and the base station decides to transmit the data in beam 2 in P2, it will be okay. But if the mobile is also making beams, then the base station is transmitting data for this mobile in a beam which the mobile can receive. So the beam in the mobile has to be directed towards the blue beam in P2.
Yeah.
Also, if the mobile is so I guess we are operating either in P2 or in P3. We are not operating in a combination.
Actually, it's in phases. You can have P1
P1
and then have P3, or you can have P1, P2, and then P3. But the point is, P3 always comes after you select your downlink beam, your TX beam from the base station.
Okay.
Once you select that, then you select the...
It can be a further step.
Yeah.
Okay.
And it's autonomous, means that once the UV selects the RX beam, it never informs anything to the GNode B. It's just him doing autonomously one decision. Because the GNode B never knows that you are operating a receiver beam.
But,
Okay.
okay, so I think we can discuss it on that.
But, so just to mention, we have a procedure. How do we maintain that? The UV is moving. We monitor the beam quality, the SINR of the modulator, monitor the SINR, and there is a threshold, 10% blur. If I'm below, sorry, 3% blur, if I cannot decode, if my blur increases beyond 3%, and I demodulate the referencing of the PDCCH, I can declare beam failure. This beam is no longer good for me, the UV. And then I have other set of beams that I'm monitoring in parallel. So I never monitor only my beam, monitor my beam and a set that I call Q1, which is the recovery beam, set of beams. If I fail, I will choose one of the other ones, and based on the received quality. Sorry? beam handover, yes. It's a kind of beam handover.
But
Which
it
I,
can be from another genome.
no, in the same cell. The same cell. So in the same cell, I monitor my beam, which I'm being served, and what they call Q1 beams, which are the recovery beams. So I monitor, let's say, 3, 4 beams. When if this fails, I already have one of the other ones to recover. So, it's a quick procedure. I'll explain there are 2 ways to do this, with contention and without contention. But it's a quick procedure in the sense that in less than 10 milliseconds, I'm back in business.
Can you say that the Q1 was a fallback from P2? If you cannot monitor one of the number beams, then you...
If I fail with beam failure recovery, I will declare radio link failure. And necessarily, we need to do a cell reselection, which we'll call. So, I'll try to skip because time is finishing. What is important here is that if I'm monitoring different reference symbols, and I still have one TRP where one reference symbol where it's good, I will not declare it. You only declare beam failure detection if all the reference symbols for that beam are failing. If all of them are failing, I send a signal to the higher layer. I have a beam failure indication. And I have to have a number of beam failure indications which is configured by the network before I declare. Okay, this is a beam failure. It's not, oh, one failure, I already declared. No, I have some filtering and I have some timer because I have a beam failure indication. If I don't have a new beam failure indication within this timer, it resets. So it was just momentaneous error. But if inside the timer I have, let's say, 5 measurements, and that's how the network configure you, for example, then you will declare beam failure, and I will trigger beam failure recovery. The beam failure recovery, we can have contention based, and we can have contention free. In the contention free, each of those CSI RSs have a specific RAG code, which I'm going to use to transmit. And if I transmit in that RAG code, the network knows, okay, that the beam, his old beam failed. He says he needs to use this other beam. So it works like a two-step RAG. This is the two-step RAG. I transmit the RAG code and immediately I recover on that new beam. Or I can content. I can transmit a RAG code using one of the available codes, such that I indicate what is the beam I need to recover, if this is not possible. How this is done? The contention free can be over SSB or CSI RSs. If it is above a certain threshold, I use contention free. If it is below a certain threshold, I will need to contend to transmit my RAG code. And the client recorder. So I basically will use RAG codes to transmit the beams that I want to recover. This is the quick mechanism for doing the beam handover. This is just explaining what I just explained to you. What is important here is that this is quick in comparison to anything else. You can recover in between 10 and 20 milliseconds from a beam failure, which is, in terms of what we are operating, is really quick. So it works. It was designed to be operated before you have radio link failure, because before you lose the link. So you are moving, you lost beam contact. This beam is no longer good, but you still have other beams that you can recover. So it's quick. You try. So it's not uncommon to have a beam failure and recover like this. Then you have a very slower mechanism operating on the same measurements. The same measurements work for different mechanisms. And this is what you already had since 2G, the radio link monitor. You're monitoring the quality of the channel, and if it goes below a certain threshold, you try to recover on a different cell. And using the same signals. So we have the same measurements, whether I'm in sync or out of sync. The only difference that with 5G now, we are doing this not on the omni signal transmitted by it's on the beams. So if we fail, we have some threshold which is lower than beam failure detection, such that we would first have the beam failure occurring and then the radio link monitor occurring. And also we have a certain number of continuous operations. We have a timer. So this needs to occur, a large number of radio link outage needs to occur within a certain time for us to declare the radio link is lost. And if the radio link is lost, we declare what is known as radio link failure. And radio link failure is something that will trigger a cell reselection, necessarily a handover. And either when the timer expires and we have measurements, when we have problems with random access in the Hierarch procedure, for example, when we are trying to do beam failure recovery and we fail n times, there is a threshold of number of times I can try beam failure recovery. And if I fail these consecutive times, I declare I need to do a cell reselection. Or at the higher layer, if you try to transmit at the higher level numerous times and it fails, you also have a radio link failure. A radio link failure necessarily will trigger a new cell reselection, a new handover, forced handover with some interruption, basically.
So if we are operating always like this, it may be for intra-cell beam selection or for inter-cell handover. We are always operating like this, that we lose the link and then we do something.
Yeah.
Is that right?
Yeah. That's the default mechanism.
And in case of inter-cell handover, how does the new cell know what part of data has been lost?
What?
Because, for example, there is a data streaming, okay? And at time t, the mobile is lost, okay? So up to time t, certain amount of data has been transmitted to the mobile. But it's a big file.
Yeah.
Okay? So how does the other side, where is it going to start?
When you are in the network, you are always anchored. Mobility is anchored on some AMF, which used to be the old mmC, which is a component in the core of the network, which knows where you are attached. This AMF knows.
So basically, this will lead to an interruption of how long?
Depends how long you need to measure to select yourself.
No, I mean in best case or worst case.
You can make a decision if you already have been measuring 20 milliseconds or less.
But then
you have the core signal.
in MFR,
Including the core signal.
20 milliseconds.
If you already had the measurements, it's just a matter of reselecting. The signaling is quick. But if you need to collect, you will need to first measure, then do the cell selection. So it may be slower. So
One last question. What is the transmission time for a block? When you say a block is transmitted, how long it is a block?
it's really quick. It's 4 FPM signals. So
Okay, it's a radio block.
a block, SSB or a burst, you mean? A burst is a sequence of blocks. One block is around 4 signals. 4 signals. 4 signals and 240 subcarriers. So it's 20 PRBs. It's very narrow, because now you can have like 400 PRBs. You can have a large number, so it's really narrow. No, it's good because then
it
make
is
an
really close
information.
to substitution, but after, in fact, we have another meeting, so 1 or 2 minutes, I don't know how many slides are left.
For example, did I answer your question about the mobility procedure?
Yes and no. I mean, of course, I didn't understand, for example, if this process is adaptable to different velocities, for example. Because if this is thin, then the beam is thin, then of course we are driving the car very fast, we lose very fast the beam. Otherwise, the beam is thicker, like, so of course we have a...
It's all decisions for the scheduler. So the scheduler.
Okay.
So it's really up to the scheduler to decide how many resources, how wide or narrow beams he wants to do, and how frequent he wants to report back. So a smart scheduler would detect your mobility speed, and based on your mobility speed, would allocate more or less resources, and would configure you to report quicker or slower the reports. So a smart scheduler would do this depending on the speed. And you need to remember that this is on top of everything that GNOD has to do on the scheduler. So there are schedulers and schedulers, but a smart scheduler will do it. Will configure differently. But you have the resources, you have the measurements. You just need to apply them for who needs. What you need to detect the mobility. Actually, there is a competition right now going on. I can send later the link to I don't know Francois, but there is a competition with a large data set of measurements from mmWave in a urban environment with car mobility and stuff, where the idea is the competition to see if you can train a machine learning, you can train a machine learning neural network or whatever to detect that before the failure occurs. So you can react first, because if you are measuring, you are reporting back to the GNOD. GNOD can make a smart selection, switch you to a different beam before you fail. But for that, it will need to have a smart algorithm doing the smart filtering or whatever, I don't know, classification or whatever. There's competition going right now, and I think Nokia is co-sponsoring this. I'm not sure where you can afford, but this is one area of research. So how we can react before the failure occurs. Yeah, that's it. I would just like to add that. Huh?
But you have a summary or?
Sorry?
You have a summary slide?
No, yeah, no, I have no. No, I had one more. But the idea is that right now what we are doing, we did this analysis because we did. The idea is with all those parameters, all those delays for measuring, all those resources that we need to allocate, that we need to spend for doing the beam monitoring and everything, will mobility work with FR2? We conducted some system simulations, especially in the context of high-speed trains. And last year, in December, we took these results to QGPP. And we actually are the only company that's taken some results. It seems that everybody standardized this, but there is no system-level results. So they standardize it out of thin air. But we are taking those results for these special scenarios, high-speed trains, and we tend to do this for others, especially for the multi-panel situation. That indeed can work, requires some smart scheduling, smart parameterization, but the network, 5GNR, very provides us the mechanism, just a way of properly configuring. But if you don't do this, then the delays make it impossible to even use the network. So you need to make use of the parameters properly. I don't know if it is something that I can tell you.
So if someone has one short question you can ask, but then I encourage you to discuss with Fuad after I think there are many people interested, so we are encouraged to discuss just after this meeting. Okay.
Now I'd like to just start because it's a lot of subjects that I try to cover in 1 hour, and but I intend to come next time with results. This